So Hi, everybody. I know there's a few people on early here. This is Ken Swilchik. I'm the moderator for today's webinar. We'll be starting up in about 10 minutes or so. We're expecting a pretty large audience today, so I want to give people plenty of time to log on and make sure they've got their computers and their Zoom up and running. So thank you for joining, and we'll be starting in just a few minutes.
Hi, good morning, everybody. Thank you to everyone who has joined already. Looks like we're getting a pretty good crowd building here. This is Andrew Filipowski. I'm one of the engineers who will be presenting today for John Crane. Just wanted to give a heads up, everything is working as planned, but we're going to give a few more minutes before we get started, just to let the last few people roll in and get up and running, and then we'll get this ball rolling here in just a couple minutes now.
Hi, everybody. It's right at 10 o'clock Central Time. Might be different where you are. I'm sure it's different where you are, depending on where you are in the world. We've got still a lot of people just joining, so I'm going to give it another minute or two before we get started in the program. It'll run about 45 minutes, so we do have a little bit of time, but I'll give another minute or two before we get started. Okay, everybody. I know I've made a few announcements here and introduced myself a bit earlier to some of you folks, but I'd like to get started now. We've got about a 45-minute program for you today, but just want to welcome everybody into another John Crane webinar. My name is Ken Swilczyk. I'm a marketing communication specialist with John Crane, and I'll be your host moderator for today. If you joined us for session one, held back in July, we'll welcome you back. If you did miss that first session, it is available on demand on the John Crane website. If you go to the resources tab, you'll find a section called webinars, and you can see our other webinars there, but you'll find this one as well. You can download it and listen in and kind of bring you up to speed on the last session. And the next session is planned for November 19th. We'll be having information about that. As a registered attendee, you'll be getting emails on it and also be on our website and social media accounts. So want to get started here before maybe some of you who are unfamiliar with John Crane. I know there's a few of you out there who may be new to us, but just to give you a brief overview, we were founded over 100 years ago and are a global leader in rotating equipment solutions. We have an outstanding reputation for design and engineering high quality, durable, customized solutions. And in 2019, we received Frost & Sullivan's Global Mechanical Seal Market Leadership Award. And just a bit of housekeeping, there will be a Q&A session at the end. If you want to submit any questions, on the bottom of your screen, there should be a Q&A tab. Just type it in there and you will be able to ask questions, and we'll get to as many as we can during the program. If we can't, we'll address them via email after the program. And also, as registered attendees, you'll receive a webinar to the recording of today's event. And if for some reason you overlook the email, it will be available on our website probably within a week or so. Just to give you a brief outline of today's session, this is session 2. As I mentioned earlier, you can access session 1 on our website. We'll be talking about interpreting the seal condition part 1, relating seal condition to the underlying causes, and we'll go through 4 of the major causes here, and then we'll also, Stewart will take you through that, and Andrew will take you through the suggested actions to ensure a long seal life, and then they'll both be available for Q&A. And then, as I said just a few minutes ago, session 3 will be scheduled for November 19th, and we'll just take you through some different additional underlying causes and actions for those, and also take live questions. Just to go through today's speakers. First speaker we have, Andrew spoke just a minute earlier. He has 5 years of experience with mechanical seals and John Crane in various field-based roles. His responsibilities have included seal and support system troubleshooting, seal performance calculations, and seal failure analysis. He has a Bachelor of Science in Mechanical Engineering from the Georgia Institute of Technology. And it's industry-wise, he's involved in pipelines and refineries in the oil and gas industry, and also the petrochemical industry. We also have Stewart Worthington. He is from our Manchester, England facility, and he has 7 years of experience in a product development role working on high-duty sealing and bespoke solutions. His areas of specialty are high-duty applications, designing and developing bespoke solutions, calculations, and troubleshooting. He holds a Bachelor of Science in Aerospace Engineering from the University of Liverpool. He also has industry experience in oil and gas. He's been a maintenance engineer in the railway industry and also a product engineer for a pump OEM. And with that, I will turn it over to Stewart, who will take you through the first portion of our program.
Thank you, Ken. This is Stewart Worthington speaking. So this session, as Ken alluded to, last time we really looked at symptoms you might see when you're looking outside the pump while it's running. This focus is going to be a lot more on seal components when we actually, after we've stripped the pump down, we've taken the seal out. But I wanted to start by just introducing a concept, which I'm calling passing geometry on to the primary seal. So what we have here is primary seal. I'm just going to zoom in, particularly on the mating ring for the moment. So as discussed in the first session, the parts of the mating ring and primary ring which are touching each other have been lapped to very flat to create that really nice fluid film between the faces. And we often lap the backs of those faces as well. However, one of the problems is that those rings have to then touch things. So here we can see the mating ring touching and pressing up against the back of the gland plate. Now, that metal gland plate is a lot harder to get and stay very flat. So if there are any sort of bumps or distortions on the gland plate, it's actually possible that as the mating ring presses against the gland plate, those bumps and distortions can be passed through and it'll affect the geometry right at the front at the primary seal, which is obviously a problem. We want to keep that fluid film very thin and very parallel. We don't want bumps or distortions or waviness. This tends to be more of a problem on either larger pumps, larger equipment. Basically, just the bigger things are, the harder it is to keep them really flat. And the other issue tends to occur on higher pressure pumps. It's basically the harder that mating ring is pressing up against that gland plate, the more likelihood that some of those bumps or distortions passing through. So it can occur on the primary ring, but generally speaking, you can see here the primary ring, it is touching a piece of metal, but instead of pressing hard against it, there's some springs behind it, and that's creating a bit more of a soft support. So it is rarer to see these kinds of issues on a primary ring. It is possible to further protect the mating ring as well. Here you can see there at the bottom, this mating ring is mounted differently. It's not directly pressing up against the gland plate, it's pressing up against an elastomer O-ring. So that is, again, a way of providing a soft support. So generally speaking, seals which are for higher pressures or larger equipment will be mounted this way. So with that in mind, if we go through and actually have a look at an example here. So what we're going to be talking about this in a few different ways, but a really common symptom, you might take the mating ring off and you might see that it has an uneven contact pattern around. I believe in the first session, this was mentioned and someone asked, how can you measure this? You'll see on the images today that actually it can be very visible when the contact pattern is uneven. But in particular, if the mating ring has these uneven contact parts where it seems to be heavy contact in one place and light contact somewhere else, and then the primary ring has a nice even wear all the way around it, that tells you that there's something happened on the mating ring. There's some kind of distortion. You can also see that image there, the primary ring at the top, and you can see there's like a heavy contact pattern there on that dimple. That is a drive dimple, which was going to pass on the drive. So that's another symptom you might see. You might see something which implies that we've had heavy loading at one of the contact spots. So we're going to look at some more specific examples, but generally speaking, if you're seeing things like this, these uneven contact patterns, it's telling you the faces weren't flat when they were running. It might have been flat when you installed it, but they've been running not flat. The seal may only leak when the pump is active and actually rotating, but equally, it might be so bad that it's even leaking when the pump is stationary. So we're going to go through some more specific examples, but really what we're looking to do here is discover what the source of that distortion is. Is it going to be something to do with the way the seal was installed? Is it something to do with the alignment of the equipment that it's installed in? Or something about the design of the seal itself? So if we go through to the next image, what we're specifically looking here is, again, we're showing a mating ring. It's got these intermittent contact patterns, and you can really see, heavy contact in a couple of spots there where it's really shiny, and everywhere else around the ring, almost no contact at all. And in particular, we're noting that this is occurring in the same, basically the same places that the bolts are located on the gland plate. So I believe we've got a picture of a typical gland plate that's about to come up. And you'll see that typically gland plates have spots for 4 gland plate bolts. If those bolts are tightened too much, they're over torqued, that'll distort the gland plate, and a really typical pattern you might see if someone over tightens one bolt, they tend to over tighten all 4. You might see 4 contact spots, but equally they may have only over tightened 1 or 2 or 3 bolts. But yeah, if you see those spots and you notice that they are in the same locations as the bolts, that really tells you that they've been over torqued. So here the remedy is quite simple. It's to, after we've had the seal reconditioned and we're putting in the new one, just make sure that those bolts are torqued up appropriately. Use a torque wrench. Don't just don't get too enthusiastic when you're installing the seal, and the problem should go away. Now, again, you can see similar thing. We've got a mating ring and we have two large contact spots. So again, if we saw two spots and they were in line with the gland plate bolts, we would check that first. But if they're not in line with the gland plate bolts, there could be a few other things which are causing this. So once again, this is the kind of thing where the primary ring might look perfectly fine, but the mating ring has these two high contact spots. It could leak while it's, well, almost definitely leak while it's running, but it could equally leak while stationary. And what we're going to consider here is, again, it could be the bolts. It could just be that the mating ring wasn't quite installed square, or there was some debris or something like that behind the mating ring, which is causing those contact spots. But another thing that we might suspect is that this is, if this was on a split case pump, it could actually be from where the split in the case hasn't been brought together with a perfect mate, which means that the surface that the sealed gland plate was resting against wasn't perfectly flat either. I believe we have, we've got an image there of a split case pump, just to put that in mind. So if we look at where the seal is installed, you can see it's installed and the gland plate rests right along that split. So split case pumps have to be assembled perfectly. It's a really important check to make sure that that surface is very even. It's common if there's issues with this to actually, after the pump's been assembled, potentially skim that surface down just to make sure it's perfectly flat and even, and it's not going to cause a 2-point distortion on the gland plate, which gets passed on to the seal. So if we see, again, slightly different, if we see one really heavy contact spot on a mating ring, so we might see some contact all the way through, but particularly we see it very heavy in one place or on one side of the mating ring, especially if it's behind a drive pin or something like that, or some kind of drive feature. That implies to us the mating ring may be out of square, and in particular, it may just be that as it was installed into its retainer or in the gland plate, it wasn't quite put in perfectly and it's just slightly kinked at an odd angle. This is equally likely to happen on the primary ring if the primary ring was installed incorrectly. However, it may not be to do with the way that the seal was installed at all. So in fact, I believe we've got an image just showing what this would look like. So you can see on that image with the mating ring, it's not quite flat anymore. Something's causing it to come at the primary ring at an angle. So it could be the way it's installed. It could be that drive pin you see just at the back isn't quite in that hole properly. It could be that there's some debris behind one spot of the mating ring. But equally, it could be that the shaft isn't perfectly aligned with the mating ring either. If the mating ring was perfectly installed, but the shaft was at an angle, then that would also cause an uneven wear on the mating ring. So as well as checking the mating ring itself, making sure there's no debris, making sure everything gets installed correctly, it's also worth checking the alignment of the pump shaft. Now, this again is an issue with a contact pattern on a mating ring. And we're calling this if you see a wide contact pattern. What you should see is the entire surface of the primary ring, in the case that the primary ring has a narrower face, the entire surface of the primary ring should have nice even wear across it. And the mating ring should have a track running around it, and the width of that track should be the same width of the nose of the primary ring. However, if you look carefully at this image, you'll see that the track on the mating ring is wider. What that's telling us is that as the primary ring and the mating ring have been rubbing against each other, they've been moving relative to each other as well. So instead of a nice constant width contact pattern, it's wider than it should be. Generally speaking, this is going to tell us that the shaft is moving, which could just be that the bearings need replacing or some other issue with the equipment. So we just need to definitely check the bearings and make sure that the seal is installed securely. And the other potential issue is if the shaft has a slight bend in it as well. That will also cause this. And then a final thing to check here is the alignment of couplings, and just make sure that we don't have any issues there which are causing extra strains or whirling on the shaft. And this image, it's a little hard to see, but this is showing an eccentric contact pattern. What that means is we have a contact pattern there on the mating ring. It's the correct width, But if you look closely, you'll see that the contact pattern is not concentric with the bore of the mating ring. It's just slightly off. So what this is telling us is that the mating ring and the shaft, or at least the mating ring and the primary ring, weren't aligned to each other. So it could be that the shaft isn't aligned properly into the center of the pump, or it could even be that when the seal was installed, the gland plate wasn't put on properly aligned in with the bore of the seal chamber housing as well. So we need to check the alignment of the installation of the seal, and also, again, checking the alignment of the shaft to make sure that it's dead center, exactly where it should be. So with that, I'm going to hand over to Andrew, and he's going to go through a lot of the alignment checks that you would do to make sure that none of these things happen.
Right, thanks for that, Stewart. So as Stewart mentioned in his section, there's a lot of evidence that we can find on mechanical seal components, particularly the mechanical seal faces, that something might be off within the equipment. And there's a number of checks that we want to do on the equipment itself before we actually get to things like alignment when we're ready to put on the coupling. So focusing just on the equipment, and for a lot of what we're going to be talking about today, we're going to be focusing on some numbers and some limits that apply to pumps, because that is the most common piece of equipment that mechanical seals are installed on. But there are a number of checks that we want to take. Definitely if we've seen this kind of damage or this kind of condition of the seal components, but really these checks should be done anytime we're going through a piece of equipment prior to any installation, even if we don't think there's going to be an issue. We're going to want to check runouts on both the shaft and possibly on the sleeve if we have a hook sleeve arrangement, if it's not a solid shaft. We're going to want to check for our radial bearing fits, checking additionally on the shaft the amount of in-play that we have, the axial movement on the shaft there. Check perpendicularity both on the face, and this is going to be the seal chamber face. We'll talk about that in more detail. Checking the perpendicularity of the frame, and then also checking for bore concentricity between the shaft and the seal chamber bore. When we're making these measurements, we're going to use runout or total indicated runout with a dial indicator setup. Runout, when we're doing shaft runout, we'll call it total indicated runout. On things like in-play or perpendicularity, where we don't necessarily have runout, you might hear it called total indicated reading, just to make it a little more accurate. But for all these measurements, we're going to be using a dial indicator, which you can see on the right side of the picture here. We'll have a base for that indicator that will either be attached to a stationary or rotating component, depending on the measurement we're trying to take. And then we'll have the tip of the needle of the indicator reading on the surface where we want that measurement to be taken. When we're taking these readings, it's possible for the needle to move in either direction. So you could get positive or negative readings. And the point with the total indicated reading or total indicator runout is we want to make sure that we're taking the highest difference between our greatest positive and our greatest negative reading. So if we go around and take a series of measurements and we read +2 and -2, the total indicator readout in that case would be 4, which would be the same as if we read 0 and 4. So it's just giving us an idea of the total amount of how far out we are on that check. So with regards to the first check here, we're taking a shaft reading or a shaft runout reading. You can see that the indicator is reading on the OD of the shaft. We're going to rotate the shaft by hand until we go all the way around, make our readings, and look for a total indicator reading of less than 0.02 of an inch or about 50 microns. Again, these are the limits or the maximum recommended values that we're going to be talking about on the next slide are focusing on pumps, pieces of equipment such as agitators, mixers, things like that, that are larger and might have more runout, might have a higher reading acceptable for them. Once we've gone through and taken our runout readings, we're now going to move on to our radial fits. On the previous reading, we were rotating the shaft around. On this reading, we're not going to be rotating. We're still going to be reading off the shaft, but what we're going to be doing is actually lifting and lowering the shaft by hand, still taking our highest positive and negative readings, and checking for the fit of our radial bearing, keeping in mind that we're going to have on most applications a bearing housing with both a radial bearing and a thrust bearing. In this case, we're going to be checking the radial bearing. The maximum recommended here is again 0.02 of an inch or 50 microns. If we're exceeding that value, we might want to check the shaft and bearing fits to see where we're getting more radial lift than we're expecting, and bring those back into spec if we find that they're outside of what they were originally supposed to be manufactured to. Next check that we're going to be taking is the in-play. So still taking a shaft measurement here, but instead of reading on the OD, we're now going to move that dial indicator to the end of the shaft. And instead of lowering and lifting the shaft, we're going to be pushing and pulling the shaft. So we're going to be checking for axial, potential axial misalignment, the amount of axial float on that shaft. So we're really going to be looking at the thrust bearing in this case instead of the radial bearing that we were looking at on the last measurement. We're going to have a slightly higher threshold for this measurement. We're now going to allow up to 0.005 of an inch or 125 microns. And any sort of, if we run into a reading that exceeds those values, we're really just mainly going to be checking our thrust bearings there to make sure that they're in good condition, that the fits for the thrust bearing are good, that we don't have excessive float or axial movement of the shaft, which can cause a considerable number of issues in operation for the seal. The next check we're going to take is on the face perpendicularity, which was the first of the two perpendicularity checks that I mentioned earlier. When we're talking about face here, we're talking about the seal chamber face, and we've included this diagram just to make it a little easier to see what we're going to be taking, where we're going to be taking that measurement. We'll see another picture on the next slide. But what you can see here is that the red dial indicator setup, we have it mounted to the shaft now. We're no longer taking a reading on the shaft. We now have the base attached to the shaft. And the end of that indicator, the tip of the indicator, is actually going to be reading along the seal chamber face. So we want to check the perpendicularity between the shaft and the seal chamber, and because that's going to directly impact the parallel status of our rotating and stationary faces. So once we have that indicator set up, we'll go through, and much like our run out readings, we're going to do a full sweep around the face, all the way around, taking note of our highest positive and negative readings. The maximum recommended value for this reading is not going to be a flat number, rather it's going to be a factor of the size of the equipment. So the maximum recommended value here is actually going to be a 0.5 thousandths of an inch per inch of the seal chamber bore, or a 0.5 micron per millimeter of the seal chamber bore. So if we were to have a 4-inch seal chamber bore, we would allow 2 thousandths run out around the seal chamber face. Stewart mentioned in his section about split line pumps and how there can be a lot of issues if those split lines are not machined and brought correctly during the building process of the pump. The face perpendicularity check here is very critical on those split line pumps in order to check that that split line was machined and those halves were brought together correctly. If we find that the face perpendicularity is out here, we'd either want to make sure that that face was machined correctly, or possibly check the frame perpendicularity as well, since that can have an impact on our face perpendicularity reading. As you can see, the setup is very similar when we're taking a frame perpendicularity. We're still mounting the dial indicator to the shaft. We've just now moved where the indicator, where that needle, the tip of the indicator is reading. But the process is going to be the same. We are going to still rotate the shaft by hand, taking the readings all the way around. But we are back to a flat maximum recommended value. In this case, it's going to be 1.5 thousandths of an inch, or about 40 microns. If this reading comes out in excess, we'd want to check potentially the seal chamber if we haven't already checked it already, if we haven't been following this order of checks, or we'd also want to go through and check our bearing frame fits to make sure that as we've been building things up, we haven't had inaccurate fits at other parts of the build that are now impacting this reading as well. The next check we're going to take is on the bore. So a similar setup to when we were checking the face perpendicularity, but now instead of taking that reading on the face of the seal chamber, we're actually going to be taking it on the ID or on the bore of the seal chamber. And this is going to be a check that'll allow us to look for concentricity between the shaft and the bore of the pump, or the bore of the seal chamber, which will be really important to, which really is important for affecting the concentricity of the primary ring and the mating ring. So thinking back to the slide that Stewart had with that eccentric wear track on the mating ring, if we saw that eccentricity, this would probably be one of the first checks that I would want to make afterwards to see if our bore and our shaft are properly aligned with each other. So much like taking the previous checks, attaching it to the shaft, rotating it around, and looking for our positive and negative readings with an allowable limit of 0.005 thousandths of an inch, or 125 microns. If we find that this reading is in excess, we might want to go through and check the seal chamber, actually go through and inspect the bore of the seal chamber to make sure that it was originally manufactured properly. If there's been any modifications that were made to it, that they were made properly, and that they weren't any uneven cuts or anything like that that was causing them, causing these higher run out readings on the bore. Additionally, we'd also want to check the bearing frame fits, make sure that possibly there's not a loose radial bearing fit that's allowing the shaft to sit lower and causing it to be offset from the seal chamber bore, which would give us some high readings on this as well. But once we've done all our checks, everything is within limits or brought within limits if it's found to be in excess. The equipment's given a clean bill of health, then we're ready to actually go through and do an installation. These are going to be the next steps to make sure that we have everything still within proper alignment within the seal, that everything goes well from here, and that we're building upon the previous success of the equipment checks to give a good, healthy, long life to the seal. The first step is going to be to lubricate the sleeve O-ring and to slide it onto the shaft. We want to make sure that we're using a lubricant that's acceptable for the O-ring material that's being used. And we also want to make sure that we only use a small amount of lubricant. There's not much lubricant is required, and we want to make sure that excessive lubricant is not put on there that might find its way to the seal faces and affect their performance later. But the key point here is that it's been slid onto the back so that when the frame comes on, we're bolting the seal chamber on now. There's enough room for the seal chamber to be bolted on without contacting the seal gland, the seal cartridge. That's important because when we're sliding that O-ring on, we want to make sure that we're having our hands only on the seal cartridge so that there's only a small amount of weight, so that if we start to hang up or snag or potentially cut or nick that O-ring, it's easier to feel it. If the entire seal chamber, the entire cover is installed on the seal already and it's pushing the seal along the shaft, there's a lot more weight now that's involved, and it's less likely that we'll feel those initial stages of a hang up or a cut or a roll of the O-ring. And so that it's possible to roll that O-ring, possible to maybe cock the entire cartridge just a little bit as we're shimmying the head cover on there if that's required. So we want to make sure that there's that separation in that space. But once we have the seal slid onto the back, we've now brought our cover up against the frame. And now we can bring those two components in together. So now we can slide the gland up against the seal chamber, and we can make sure that the gland bolts pass through and bolt them together. So now we have connected the stationary components of the seal to the stationary components of the pump. Once that has been completed, we also want to make sure that the gland bolt or the gland porting, any piping or tubing connections that we need to make, that those ports are located at the right location. We don't want to get all the way through this and then realize we need to rotate the gland 90 degrees or 180 degrees. So it's best to make sure that those are all located properly now before we go through the next steps. Once that has been properly located, it's now time to attach the impeller. Again, keeping in mind that with some of these steps, it might be slightly different between the type of pump that we're dealing with. In this case, we're looking at a single stage overhung pump that's a in, pull out. It makes some of these components or some of these steps a little bit different than you might see on a between bearing pump or like a vertical turbine pump. But for this step, we now be bringing the impeller onto the shaft and attaching it. Once that has been completed, we can now bring the casing onto the pump and then complete at this point the build of the stationary components of the pump. Once this has been completed, the last step we're going to do from the pump side is make any necessary impeller adjustments. So if we have a pump such as this with a threaded impeller where we're able to adjust the impeller axially in and out to set it to the proper clearances per the pump OEM specs. And then once all those impeller adjustments have been made, the pump build is now complete. We're now down to the final two steps for the cartridge seal. The first thing we're going to do is we're going to tighten down these set screws to the shaft. So this will connect the rotating components of the seal to the rotating components of the pump. And then the very last thing we want to do, once we've determined that everything is set up correctly and we're ready to run, is at that point we can remove our spacer clips. Up until this point, the spacer clips have been installed on the cartridge to set the seal at the proper working height to make sure that we have the proper location for the spring or the load element within the seal. So if there's any adjustments that would need to be made, they should be done before this. At this point, everything is locked into place. The clips can come out. The seal is ready to run. So now that we've gone through, we've done equipment checks on the pump. We've done our seal installation. All of the pump is built up, or the driven component has been completely built up. We've checked for any potential concentricity problems, any alignment problems or distortion problems that could come from that end. We've given it a clean bill of health. There are a few more checks we want to make. Stewart mentioned in his section, there's a couple of potential damage or signs of misalignment that we can see on the seal that could be related to the coupling alignment. And this is the step now, or the part of the installation now, where we want to look for those. So when we're bringing our driver and our driven together, which we do through the coupling, we want to check for a few different types of misalignment. We want to check for axial misalignment between the shafts. We want to check for lateral offset misalignment or parallel offset misalignment between the shafts. And then we also want to look for angular misalignment between the shafts. Any of these types of misalignment can have an effect on the way that the rotating and stationary faces within the seal can interact with each other or align with each other. If we have large amounts of axial misalignment, the load element could either be over-compressed or under-compressed, so we could have very high loading on the seal, potentially very high contact at the seal, or it could be so far off that we actually don't get contact, that the springs are past their free height. We're not getting any spring load, and there's potential for high leakage as a result of that. If we see parallel or that lateral offset misalignment, we'll likely see eccentricity, or that offset that Stewart showed where we had the wear track off center on the mating ring. So that would be a sign that we might have some parallel or lateral offset that needs to be brought within spec. And then if we have angular misalignment between the faces, that can have the primary ring and the mating ring no longer in parallel. So you might have the angle, and Stewart mentioned in his, if you have that angular offset with the mating ring and you see the really high contact at one point on the mating ring, that's a sign that the faces are no longer in parallel. There's that angular offset between them, causing that high contact at that one location. Conversely, the other side of the face has lower contact, possibly even no contact. It's going to have a wider gap between the faces, and we'll likely see a higher amount of leakage as a result of that. So all of those should be taken. They can be done in a number of methods, whether you're using dial indicators or possibly a laser alignment system. And then once the driver and the driven part of the equipment are brought within their alignment, at that point we're ready to install the coupling, and the equipment is ready to run, and should lead to a longer and better performing seal. And with that, I will turn things back over to Ken.
Okay, thanks Stewart, and thanks Andrew for a very informative presentation. Yeah, so now we've got about a little over 10 minutes left to take questions. Again, if you want to submit questions, you can use the Q&A button in the center of the bottom portion of your screen. Just type your question in and we'll address it. And we do have a couple of questions that came in during the program. Stewart, if you could handle this one. First question we have is, are there types of pumps or equipment where higher amounts of misalignment would be expected?
Yes, absolutely. So I guess the first thought that we would have, that we might suspect higher misalignment, generally, it does tend to come with size. So the bigger the shaft is, the harder it is to get perfect alignment. Of course, there are types of really high precision equipment, things like large turbo compressors, which would also have really high grade bearings that would keep things quite centralized. But apart from that, anything with larger shaft, we would expect a higher misalignment. And typically that might be things like large vessel or mixer seals would have to deal with that. I'm also thinking about boiler feed pumps for power generation. And often a lot of pipeline seals as well. They all tend to have large shafts, and we know to expect we may have higher shaft misalignment.
Okay, thank you, Stewart. We do have another one that came in. Andrew, if you can address this one. The question is, are there seal designs that can accommodate higher amounts of misalignment?
Yeah, sure, Ken. So as Stewart mentioned, there are pieces of equipment where we expect higher amounts of misalignment. So it would make sense that we would be ready for a seal design or aspects of a seal design that could handle that amount of misalignment. So for things like mixers and agitators and those larger vessel types of equipment, we do have seals that are intended for those kinds of services. With those seals, we typically design faces to accommodate for higher amounts of misalignment. There's more room on both the ID and OD of the nose of the primary ring to maintain tracking on the mating ring. Additionally, we're also going to open up clearances within the seal so that we reduce the chance of rubbing between rotating and stationary components of a pump. And we'll also look at the flexible elements and the load elements that we're using as well to make sure that they're more accommodating for those high amounts of misalignment, less likely of things like cyclic failure going through those large axial movements that can result from the misalignment as well.
Okay, thanks, Andrew. Got a couple more questions here we can go through. Stewart, if you can handle this one. The question is how to decide the amount of tension for a pusher spring.
Sure, absolutely. So the springs in a pusher seal, their primary job is really just to hold the faces together while the pump isn't running. So they don't actually need to be a particularly high force. And if anything, the more force we have, the harder they're being pushed together. So when things do start to run, that would lead to higher wear. So what we're trying to normally do is figure out how small can we make that force. So it needs to be strong enough to overcome the friction in the O-rings so it can push the primary ring backward and forward. But the other thing it needs to be able to do, particularly on a single seal, it needs to be able to make sure that if there was ever a vacuum in the pump, that vacuum would try and pull the seal faces apart. So the springs need to be stronger than a full vacuum in the pump. So as long as we've done that, generally speaking, the spring should be strong enough. Generally, yeah, we're looking at quite low spring forces.
Okay, thanks, Stewart. Got another question here. Andrew, I don't know if you can take this one, but it says, do seals on vertical shafts see similar problems, and are they better or worse?
Yeah, so vertical shafts definitely have run into the same, at least general kinds of issues, same kind of misalignment potential concerns there. You're not going to see a split line vertical pump, so you do get rid of some of the issues that are considered with an axially split pump. But they come with their own set of issues as well. So there's certain vertical pump arrangements that might only be supported by the motor bearings, and in those cases, they're more susceptible to run out or exceeding the loads of those bearings. So that's an issue as well. And additionally, with vertical pumps and vertical shafts, you tend to be dealing with a much longer shaft, and so you have a greater chance for run out or whip on that shaft, especially if you have anything building up on the impeller that's causing some imbalance there. So vertical pieces of equipment run into the same issues, and I would almost say that vertical pieces of equipment often sometimes run into more issues with regards to these misalignment concerns.
Okay, thanks, Andrew. Just going through another question here. Stewart, you can maybe address this one. It says, besides pump condition, are misalignment and pump strain the main culprits of leaking seals?
Well, I would say it's more that it's been very much the theme for today has been all about misalignment. So we don't want to necessarily give you the impression that's the only cause, but we will say that installation is a really critical time for the seal, and it does account for a fairly high proportion of seal failures. I wouldn't want to hazard a guess how many, but we do find it's a significant portion of seal leaks do tend to come from either issues with the alignment in the equipment or issues with the way that they were installed.
Okay, thank you, Stewart. Just looking through some of the questions here, Andrew, I'll take this one. I know this was I think this was addressed in the last session, but it's probably a common question. It says, even with a well-installed seal, what amount of leakage could we expect? Is it easier to detect the difference in leakage between a well-installed seal and not one so well-installed? You could address that, Andrew.
Right, so all seals will leak some amount, and we did talk about this a little bit in the previous session. All seals by design have to leak some amount. Now, normally for the majority of services, it's an amount of leakage that's probably not even noticeable, definitely not noticeable visually. And it'll depend a little bit on the service. What's the process fluid that's leaking, or what is the fluid that's leaking? How much pressure is the seal under? Some other factors of the seal design itself. But for most well-running, well-maintained seals, the leakage will not be noticeable. For seals that are not installed properly or have high amounts of misalignment, the amount of leakage is usually pretty noticeable. And so there is usually a pretty easy to see discrepancy between the leakage amount of a well-installed, well-aligned seal versus a seal that was not well-installed or not well-aligned on a piece of equipment that's not well-aligned.
Okay, thanks, Andrew. Got another one for Stewart here. Do you see any seal issues associated with speed changes due to VFW drives?
Yes, yeah, that is something which is an increasingly hot topic in the seal world, as using variable frequency drives to, well, vary the speed of equipment during service. It's becoming more popular because of the efficiency gains in the actual equipment itself. The issues that we see tend to be around the fact that seals really like a good constant speed. They don't like it when you start and stop them. For the seal, the perfect life is to get up to its maximum best operating condition and just stay there, continuously running. So yeah, every time we change the speed, it just does maybe a little bit more wear to the seal than if it had stayed continuous. The other thing that we sometimes see is that with variable frequency drives, operators are more tempted to run outside of their best efficiency points of the equipment, which also has a knock-on effect on seal life.
Okay, thank you, Stuart. We got a couple minutes left here, so I will take one or two more. Andrew, it says here, how do you check the spring tension for confirming good or bad condition?
Right. So you're not normally going to check the spring tension directly once the seal is installed. It's very difficult to actually gauge that. When the seal is being assembled, we can check the tension on the spring using a press and checking the amount of load that the spring applies. As far as checking spring tension in the field, your best bet, if it's a cartridge seal, is to check the spacers or the setting clips on the seal and make sure that they could still slide into their original slot, whether it be on the shaft or the collar, depending on the design, but make sure that they still slide into their original location. That will tell you that the seal is still set at its original desired working height. And so the spring is at its working height. It should have the proper load applied to the seal at that point.
Okay, looks like we've got time for one more here. And I'll check this one here. I don't know, Stuart, if you can address this one. It says, during the presentation, it was shown to check the flatness of the surface where the seal is installed, 0.005 inch dial, but also the flatness of the casing. Is there a particular reason to check the last surface? Because it looks like it does not affect the insulation of the seal.
Sure, I guess I can. Is
that one better for Andrew, or?
Andrew's going to be more of the expert in that one because he'll remember what the last image was, unless you want to pull it up, Ken.
No, I think I can take this one.
Sure.
So this is talking about taking the face perpendicularity check on the seal chamber face and then taking the frame perpendicularity check as well. The reason being kind of actually ties in a little bit to what Stewart was mentioning with his part of, as the distortion on the back of the gland plate on the back of a mating ring can affect the distortion on the face of the mating ring. Similarly, if we've gone through and taken our seal chamber face runout readings and we find that those exceed values, one thing that we can also check is the frame perpendicularity, because the frame will affect how the seal chamber is installed. If the frame itself is not perpendicular with the shaft, it's possible that that will cause the seal chamber face to also not be perpendicular. If we check the seal chamber face and we find that it is perpendicular, most of the time, no, we do not need to check the frame perpendicularity as well. It's just an additional check to take if the seal chamber face perpendicularity does not check out.
Okay, well, thanks everybody. That was, thanks Andrew and Stewart for your presentation, and thanks everybody for signing on here. We're just about out of time, and if we have any other questions that come in, we'll address them to you via email. But I appreciate everybody joining, and thanks for taking part. Keep an eye out for the next webinar, which will be taking place on November 19th, which will go through some more conditions and how to correct them. So again, appreciate everybody signing on and appreciate all your questions and attention. And everybody have a good day.